Hi everyone, in this lesson, now that we've covered separation of variables and talked a bit about differential equations in general, we're going to look at a specific type of differential equation, and it's known as a linear differential equation. And these equations have a very specific form. Okay, so your first term is dy by dx. Your second term is a function of x only, so p of x times y. It's important that it's just multiplied by y. And on the right-hand side, you have just a function of x. So we're calling p of x and q of x just functions of x. Okay? If you want to look at what this looks like in terms of a real example, instead of p of x and q of x, if we have dy by dx plus 1 over x times y is equal to 2x. In this case, p of x is the term behind the y term, which is 1 over x. Q of x is equal to 2x. Okay? A couple items to note here. You have to have dy by dx by itself in this form. So if there's anything behind it, like an x term or a 2 or 3 or a number or something, you have to divide every term by that. Okay, so you have to have dy by dx by itself. The next item to note here is that your function in the middle here has to be multiplied by y. Okay, y only. It can't be y squared or y cubed, etc. Okay. The third item to note is in your third term, it has to be a function of x only. So it's going to have numbers and some x function. Okay, so this can't be 2xy. Okay, it can't be 2x plus y. It can't be any of those functions. So if your equation starts to look like that, okay, if you're given a question and it looks not exactly in this form, you may have to do some rearranging. Okay, so just keep that in mind when you start looking at questions. So we're going to look, and I'm going to show you this example, and I'm going to show you how to solve it. And the first item to know is that in order to solve it, we have to use something called an integrating factor. And for these types of equations, the integrating factor, okay, is e to the exponent. The exponent is the integral of that p of x function. So remember, we had dy by dx plus p of x times y is equal to q of x. So whatever you have for p of x here, okay, I'll change colors. That is what gets substituted into this integrating factor. So this integrating factor is key to solving these equations. I'll show you how to solve it using it, and I'll give you kind of a brief overview as I'm solving as to why this integrating factor works. But if you do want to know the derivation, I can actually show you. So you just have to ask, okay? But I won't show you for the purposes of this lesson. So if we go back to this equation, this integrating factor gets multiplied, both sides get multiplied by it. Okay, so you're going to have e to the integral of p of x dx multiplied by this, and e to the integral of p of x dx multiplied to the right-hand side. Okay, remember, because whatever you do to the left-hand side of the equation, you have to do to the right-hand side of the equation. Okay, so it's just, that's the fundamental rule. So it doesn't matter that you're adding this factor as long as you do it to both sides. So remember, p of x in this case was 1 over x. So if we substitute that in, we get e to the integral of p of x dx is e to the integral of 1 over x dx. Remember, we have 1 over x, right? X to the exponent 1. The integral of that is ln. So e to the ln of x happens to just be x. Okay? So that's just, an identity to know with e, because you have an e and a ln. So in this case, we end up with just x. Okay? Once we do that, we can take that value of x and we multiply both sides by it. So we end up with x times dy by dx plus x times the 1 over x times y term. And that's equal to, on the other side, we had 2x times x, which gives us 2x squared. Okay? So if we simplify this, the one simplification we can do is we have an x divided by x, which cancels. So we're left with, on the left-hand side, x times dy by dx plus y is equal to 2x squared. So what I want to show you, I don't expect you to look at this right now and think, oh yeah, this was automatically the product rule. But when you're solving these equations, what you're going to notice is because we multiply by that specific integrating factor, remember, our base equation looks something like this. Okay? And our integrating factor is e to the integral of p of x dx. So when we multiply by both sides by this integrating factor, what we end up creating is on the left-hand side, we actually have the product rule. So if you remember the product rule, the derivative of two functions multiplied together, so in this case x times y, and we'll do it with respect to x, is equal to the first term, which is x, multiplied by the derivative of the second term, dy by dx, plus the second term, which is y, multiplied by the derivative of the first term, which is dx divided by dx in this case. Okay, so in our case we have here, dx divided by dx is just 1, right? It's the same term on the numerator and the denominator, so that cancels. And what we end up with is x times dy by dx plus y. Okay, so what you notice is if you do the integrating factor correctly, your left-hand side will always simplify to the product rule. Okay, so that's an important item for you to keep in mind, is that's what you're ultimately looking for. So your challenge in this question is to determine what x and y are in the question. Okay, determining what those two factors are, because what happens is we go from this, which is what we have in our equation up here, and we substitute in what we started with initially. Okay, so when you look at the product rule, it's the derivative of the function x times y with respect to, in this case, x, right? Because all of our functions are x. So what we do is, like I said, instead of what we had on the left-hand side, which was x times dy by dx plus y, we substitute in that original form for the product rule. So the derivative of the two functions, x times y with respect to x, right? Because it's the same thing. And when we do that, if you remember back to when we did integrals, okay? A lot of times when we were doing substitution, we moved one of these terms, and usually the dx term, to the other side. So we're going to do that here. So there's an intermediate step here where we have derivative of x times y is equal to 2x squared dx. Okay? So now, on both sides of our equation, we have a dx term, or a d term. This is dx, this is dx times y. So we can take the integral of it. Okay? So on the left-hand side, the integral of that derivative, x times y, is just the function we started with. Remember, using the product rule, we started with a function that was two items multiplied together. So you end up with the derivative, or the integral, of the left-hand side is just those two functions multiplied together. The derivative of the right-hand side, in this case, we used the integral of 2x squared dx. So the integral for that is just x cubed, and then plus the constant. So remember, in these questions, we always add the constant at the end. So now, if you want to solve for the initial function y, we just divide both sides by x, right? So we end up with y by itself here. And if we do that, okay, these x's cancel, this x becomes x squared, and this last term becomes c over x. So we end up as our final solution of y equals x squared plus c divided by x, okay, because we don't know what that constant is. So I'm going to walk through some examples now where you're going to start to see the pattern as to how I pick out what the x and y values are for this product rule, because that really is the key to being able to solve these questions regularly, okay, or getting more proficient at solving them. Okay, so let's look at our first example. Solve the differential equation dy by dx plus 3x squared y is equal to 6x squared. So starting with the basic version of the formula, dy by dx plus p of x times y is equal to q of x. So looking at this, we see that we have just y here, which matches with this, and a function here that's just a function of x. So that means that p of x must be 3x squared. On the right-hand side, we have just a function of x, meaning q of x must be 6x squared. Okay? The thing that I omitted here to mention is that behind the dy by dx term is nothing, which is consistent with the basic version of this formula. So what this means is that starting with our integrating factor, e to the integral of p of x dx is equal to e to the integral of 3x squared dx, which is the integral of this is 3 times, remember using the power rule, 1 over 2 plus 1, or the exponent plus 1, times x to the exponent 2 plus 1. So you'll have a 3 in the numerator, and 2 plus 1 is 3 in the denominator, which cancels. So this becomes e to the x cubed. So now we can multiply both sides of this initial differential equation. We'll move those brackets to make it easier to see. And what we have is e to the x cubed times dy by dx plus 3x squared times y is equal to 6x squared times e to the x cubed. So if we multiply this in, I'll write it over here, we get e to the x cubed dy by dx plus 3x squared e to the x cubed times y, which is equal to 6x squared e to the x cubed. Now remember what I said, on the left-hand side, it will always be the product rule. And the trick in this is determining what the two variables are. Remember, the one function multiplied by the other. And one item that I will show you here, or a trick, one of these will always be y. Okay? So one will always be y. The second one is usually that function e. Okay, so e to the x cubed in this case should be the second variable. So your integrating factor is usually what becomes the second variable. And to prove that, what I'm going to do is I'm going to show you why that's the case. Okay, so we know that the one variable is always going to be y. We want to look at the other one. Okay, we're going to look at specifically this term here. Okay, so remember that we have the product rule, derivative of two functions, x times y, with respect to x, is the first function, x, multiplied by the derivative, dy by dx, plus the second function, y, multiplied by the derivative of the first function, in this case, dx, or dx. We don't know what the function x is. We just know that there's two functions. So if we applied that rule here, and we used what I told you, where x, okay, the first function is that integrating factor, e to the x cubed, And the second y is simply y, okay? And you'll notice that it's going to be the case. If we do the product rule on this, okay, we have the first function x, which is e to the x cubed, times the derivative of the second function. We can just leave it as dy by dx, okay, because it's the function y. For the second function, we have the function y, which is y, times the derivative of the first function. And the derivative of e to the x cubed is, remember, e to the x cubed times the derivative of whatever's in the exponent, which is 3x squared. Okay? Now what you notice is this is actually the same as what we have here. Okay? So e to the x cubed dy by dx plus the 3x squared e to the x cubed times y. So the reason I show you this is this is a quick way for you to determine what those two functions are. It will be y and your integrating factor. So if we write it out this way, we get the derivative of our integrating factor, e to the x cubed, times our second function, which is y, and that's all with respect to x, is equal to what we have on the right-hand side of the equation, which is 6x squared e to the x cubed. Okay? So remember, like I did in the example, I moved the dx term to the right-hand side, and that's so I can integrate both sides. So if I do that, I get the derivative of e to the x cubed times y is equal to 6x squared e to the x cubed dx. So now I can take the integral of both sides. So if I take the integral of both, remember the integral of this product rule or derivative is simply what's in the brackets. So on the left hand side, this just becomes e to the x cubed times y. On the right hand side, I'm actually going to use substitution. And I'm going to do it in a different color. I'm going to let u be equal to, remember, in substitution, I usually made it equal to the more advanced function, which in this case is e to the x cubed. So du by dx is equal to, remember, we did this derivative already over here. We have 3x squared e to the x cubed. Okay, so it's e to the x cubed multiplied by the derivative of that exponent. So if we substitute it in, we'll move the dx term once again to the right-hand side, and we get that du is 3x squared e to the x cubed dx. Okay? Substituting that in, see we have a 6x squared here and a 3 there, so that means we have 2 as a residual. So we're left with the integral of 2 times u is e to the x cubed. In this case, it doesn't matter. We're left with 2 times du. Okay? Because we've substituted in for the x squared e to the x cubed dx term. Okay? Integrating that side, we get e to the x cubed dot y is equal to 2u plus, in this case, a constant, where u is an initial function e to the x cubed. So if I substitute that in, I get e to the x cubed times y is equal to 2e to the x cubed plus a constant. Solving for just y, we have to divide both sides by e to the x cubed. So they'll cancel in these two expressions, and what we're left with is y is equal to just 2 plus the constant divided by e to the x cubed. Okay? So remember, the main takeaway from this is when you're doing the product rule, it's usually going to be y and whatever your integrating factor is on the left-hand side of this equation. That's how it's going to simplify. Okay? The reason for that is the choice of the integrating factor being what it is. Again, if you want me to do the derivation as to why that's the case, I can, but just understand that that integrating factor is key to why this entire structure of the question works. So let's look at a second example. Solve the differential equation x squared dy by dx plus x times y equals 1. So I always like to start by writing out the basic form. Dy by dx plus p of x times y is equal to q of x. So we notice here that our middle function seems to be okay because it's only multiplied by y. But we have an x squared term behind the dy by dx term. So remember, it has to be dy by dx by itself. So we start off by dividing both sides by that x squared term, so that we have just dy by dx. So dividing all our terms by x squared, they will cancel in the first term. X divided by x squared just leaves us with 1 over x. So what this becomes is dy by dx plus 1 over x times y is equal to 1 over x squared. So now we see that dy by dx is by itself. We have a 1 over x term behind our y term, and it's just y by itself, not y squared or anything else, so that's fine. And our term on the right is just a function of x, 1 over x squared. So what that means is, I'll change back to my red. Our p of x function is what's behind the y term, which is 1 over x. Our q of x term is 1 over x squared. I always like to identify those so that I know that my equation is now in the correct form. So now that it's in the correct form, I can find my integrating factor. Remember, the two most important terms you're going to find out are y and your integrating factor when you're dealing with the left-hand side of the equation. So our integrating factor is e to the integral of p of x dx, which is e to the integral of p of x, which is 1 over x, times dx. That integral is e to the ln of x, okay, because the integral of 1 over x is ln x, and e to the ln of a function is simply whatever is inside the ln function. So this is just equal to x, okay? So my integrating factor is just x here. So if I multiply both sides by that integrating factor x, we get x, that's a bad x, x times dy by dx plus 1 over x times y is equal to 1 over x squared times x. So on the left-hand side, this x and the 1 over x will cancel for the y term. So we're left with x dy by dx plus y is equal to just x and x squared cancel to 1 divided by x. So on the left-hand side, remember what I told you. You have to convert the left-hand side using product rule. And what I told you is the two functions for the product rule will usually be y, okay, which we see here, and whatever your integrating factor is, which in this case is x. So using that rule, okay, I'm going to simplify this. So instead of everything on the right-hand side, remember our product rule, derivative of two functions multiplied together, x times y, is equal to the first function times the derivative of the second function, x times dy by dx, plus the second function times the derivative of the first function, which is dx by dx. In this case, our basic form of product rule actually would equate to exactly what we see here, okay? Besides the point, I want you to understand that the factors to use here are going to be y and your integrating factor. So if I change this, it now says the derivative of our two functions. The integrating factor is x, and we're multiplying by the function y. And again, it's respect to x, because our basic function we started with was with respect to x. So that has to now be equal to what's left on the right-hand side, which is 1 over x. So just like we did in the past, we're going to move the dx term to the right-hand side. So we get the derivative of x times y is equal to 1 over x times dx. So now we can take the integral of both sides. Remember, on the left-hand side, the integral of this is just the functions that we started with inside the brackets. So we're left with x times y is equal to the integral of this term, which is the ln of x. Okay, remembering it's the absolute value, plus a constant. Okay, so solving for, remember, our last step now is to solve for y. So to do that, we have to divide every term by x. Okay, so the x's on the left-hand side cancel, and we're left with y is equal to the ln of x divided by x, plus our constant divided by x. Okay, so you can see I followed the same method here that I did in the first example. Okay, all of these I had as functions of x. Our next example, we're going to look at kind of applying this. You'll see that, this equation still works, whether it's derivative with respect to x or t or theta or whatever they are in the different examples that we've seen. Okay, so our last example, changing it up a little bit, not putting a function with respect to x. Just want to show you that the process remains the same. Okay, so in this instance, we'll do a basic electric circuit. Okay, solve the differential equation L di by dt plus R times I is equal to E with respect to t, or a function with respect to t. For the circuit provided below, which I'm going to draw, the voltage provided is 60 volts, resistance is 12 ohms, and inductance is 4 henries. Okay, so we've got a basic circuit here. Okay, we've got an energy source, a resistance of some kind, inductance, okay, and a switch. Okay, disregard that I'm showing the switch open just to show you it. Okay, so this has the inductance value L that we have provided here, which is 4. This has the resistance of 12 ohms. And our energy source, E with respect to t, that we're providing is 60 volts. So given this equation, what this is showing, okay, is our voltage is equal to what's going through the resistor plus the change in current, okay, over the inductor times the inductance. Okay, just a basic circuits equation. I'm sure you've all seen it hundreds of times in some way, shape, or form. So the equation is L di by dt plus Ri is equal to E of t. Okay, so if we substitute in the values that we know, we get 4 di by dt plus 12i is equal to, in this case, 60. Okay, so instead of y here, we have I, or the current. And instead of functions of x here, we have functions of t. So I like to write it as, instead of x, we're calling all of our x terms t, and all of our y terms are I. Okay, so knowing that, we still don't have this in a base form. We don't have it. We have I here and di by dt, but we have a value 4 behind the di by dt. So we have to divide both sides by 4. Okay, so that we have it just in our basic form, which I'll write in a second. If we do that, we get di by dt plus 3i is equal to 15. Okay, remember, our base form is dy by dx plus p of x times y is equal to q of x. If you substitute in our values we're using, which is t or time for x, and I for y, okay, this actually becomes di by dt plus our function p of t times I is equal to q of t. Okay, so now our equation satisfies it. Remember, we can have just a constant here, the 3 and the 15, and they can still just be functions of t. Okay, so if we have this, we now follow the same steps. So we have to find our integrating factor. So our integrating factor, e to the integral of, in this case, I can say p of x, but it's easier if I say p of t, okay, because t is the variable we're using in this equation. So we have p as a function of t dt, which is e to the integral of, in this case, p of t is 3. So I have 3 dt, which is e to the 3t. Okay, doing simply the integral of a constant 3. Multiplying both sides by that integrating factor, we get e to the 3t di by dt plus our second term, which is e to the 3t times 3I, and that's equal to 15 times e to the 3t. Now remember, it still follows the same format. The left-hand side we have to convert to the product rule. And we always use our function y, which in this case, remember, is I, and our integrating factor, which is e to the 3t. So if we do that, we get the derivative of our two functions, e to the 3t times I, divided by, or with respect to t, so by dt, is equal to 15 e to the 3t. Okay, so remember, our next step is to move the dt to the other side. So I'll move it here just so we have some space. And we get derivative of e to the 3t times I is equal to 15 times e to the 3t dt. Okay, so now we can integrate this, okay, just following the same format. So we integrate both sides. Remember, the integral of the left-hand side is just what we started with if we had the product rule, which is e to the 3t times I. For the right-hand side, we can use the product rule, okay, if you want. So we can have let u equal e to the 3t. So du would be equal to the derivative of this, which is 3, it's the derivative of the exponent, e to the 3t, and dt. So we have a 15 here, meaning that not all of that constant will go away when we substitute in. But if we substitute in, we get 5 times the integral of just du. Remember, because we substituted in for all of those terms when we substituted in du. So integrating this, we get e to the 3t times I is equal to 5 times u plus a constant. Okay. Substituting that in, e to the 3t times I is equal to 5 e to the 3t plus a constant. Solving for I, we divide both sides by e to the 3t. And we get that I is equal to, it cancels here. Okay, these e to the 3t's cancel for the first term. So we get 5 plus our constant divided by e to the 3t. Okay, so I just wanted to show you this example to show that it applies to more than just functions, y as a function of x. Okay, equations such as that. You can apply it in multiple different areas. So before we move to the next item in this lesson, I provided a summary over this slide and the next slide of the steps you need to take to solve these linear differential equations. I've walked you through them in examples and explained them, but this is kind of an easy reference for you to remember how to solve these. Okay, so our first step was always to determine if the function fits this form. Remember, in our second example, and our third example, we had to rearrange so that we had just the derivative function, whether it was dy by dx or when we had di by dt. The second function had to have that function y, or in the case we had I, by itself. Can't be y squared, can't be y cubed. And it's multiplied by some function of x. Okay? And that has to be equal to, on the right-hand side, just a function of x. You can't have y or whatever other variable over there. It's just a function of x. Once you do that, you have it in that form, you determine what your p of x function is, and you find your integrating factor, which is e to the integral of that function p of x dx. Okay? Once you determine that integrating factor, you substitute it in by multiplying both sides by that integrating factor. Remember, what you can do to, you can multiply both sides by anything as long as you do the same thing on both sides of the equation, and that's all we're doing here. Okay? Usually this e function simplifies to something a little simpler than what I show, but this is just the basic form. After you do that, remember you have to convert the left-hand side of the equation using the product rule. And I provided you this hint, okay, that it follows the format listed below. Okay? What I mean by that is the two variables that are inside this brackets for the product rule are always going to be y, or whatever that function might be when it was I in our last example, multiplied by your integrating factor. Okay, so I show the integrating factor in the basic form, but you've seen it look, be e to the x cubed, or maybe it's just x. Okay, it depends on whatever that integrating factor is what the second term is here. On the right-hand side, what you end up with is your function q of x, okay, which it hasn't changed, multiplied by that integrating factor. Your final step, okay, is to integrate both sides. So on the left-hand side, you're always going to be left with y times your integrating factor, or again, whatever the variable is for y, and it's equal to the integral of the q of x e to the, or q of x times your integrating factor on the right-hand side. Don't forget to add the constant, and then your last step is to solve for y, okay? Normally that's by dividing both sides by your integrating factor, okay? And doing the same thing on this side, okay? So this, again, this is just meant to help you if you're looking for kind of a quick synopsis when you're studying to figure out what steps to take to solve these equations. So now I want to look at first order equations, but I want to look at equations where, sometimes you just can't solve them mathematically. Okay, so we've been able to use, in this lesson, an integrating factor to solve this. But sometimes you have to solve them numerically. And I'm going to introduce to you two methods. The first on this slide is called Euler's method. And then I'm going to, the second method is known as the Runge-Kutta method. Okay, so this method, the Euler's method first, is a little bit simpler to calculate, and it relies on a concept that we already know when we talk about derivatives. Okay, so when we talked about derivatives, we found the slope of the line that was tangent to the curve. Okay, so if you have a function here, if it's shown here as f at x, but maybe it's f at x and y, so it's dependent on both. And you had a point here that was tangent to it, okay, meaning it only touched the curve once. You could find the slope of that line. What we're going to do is use that principle in Euler's method, and what we're going to do is if we have a differential equation, so dy by dx, and it's equal to some function of x and y. So for example, we had dy by dx is equal to xy, would be, I guess, the simplest solution to that. And we know a point on this curve or on this function, whether it's a point like 1 and 3. We can use Euler's method, and we can use a step value. In other words, a small increment of x, okay, to go further and further to it. So if we know the value when x is 1 and y is 3, okay, what about when y is 3.2. Okay, we can use a step value. So let's say we can go in increments of 0.1. So if we know this, we could first find the value at y equals 3.1 and do it again to find the value at y equals 3.2. Okay, this is very similar to what you saw when we talked about doing slopes for points that were tangent to a curve. Okay, to solve this, what we do is we have our step value, okay, and we have our function y at the next point, n plus 1, is equal to y at the previous point plus that step value, which we're calling h, multiplied by our function when we substitute in those current values of x and y that we know. So in this case, we would substitute in at the start, x is 1 and y is 3. Our initial value for y would be 3. And our step value here would be the 0.1 that I talked about here. Okay, so I'm just showing you this to explain to you some of these formulas. Again, they're formulas that will be provided to you. But I want to jump right into an example where you can really see how this is used. So we're going to do one example of Euler's method before we talk about the second method, which is much more complicated but more exact. So first, using Euler's method, for the differential equation, dy by dx is equal to 0.1 times the root of y plus 0.4x squared, which passes through x and y is equal to 2 and 4. Find an approximate value when x equals 2.1 if the step value h is equal to 0.05. So we start off with a value for x equal to 2. And our step value is only 0.5, meaning we're going to then find the value for x and y when x is 2.05, and we don't know what y is. Then we're going to use that to find our value when x is 2.1 and our value of y. Okay, so we're going to step, meaning we have to do Euler's method calculations twice. So we know our formula, remember, we have dy by dx is equal to some function of x and y. And we see here this is a function of both x and y. There's an x squared term here and a root of y term here. So if we look at Euler's method, the next value of y to the n plus 1, is equal to the current value of y plus our step value h times our function at our current values of x and y. So x of n and y of n. Now what we know in here is that our first values, okay, we'll call them x0 and y0, are equal to 2 and 4. And our value of h, in this case, is 0.05. So our first value to calculate is y to the n plus 1, which is 0 plus 1, or y1 is equal to y0 plus h, which is 0.05, f at our first point, x0 and y0. Okay, so if we do that, we get that y1 is equal to our first point of y, which is 4, plus 0.05 times our function, which is 0.1 times the root of y, so it's the root of what our current y point is, which is 4, plus 0.4 times our current x point, which is 2 squared. So our initial point for y is equal to, if we calculate that out, 4.09. Okay, and that is when, remember, we have a step value of 0.05. So that is when x1 is equal to our original x plus our step value h, or 2 plus 0.05. So x1 is equal to 2.05. But remember, we're looking for x equal to 2.1. So we have to go one additional step value. So we use it again. So we get y2 is equal to our previous y that we knew, which is y1, plus again our step value times our function at our now current point, which is x1 and y1. Okay, we're inching closer and closer to that new point. Okay, and the smaller the step value, the more accurate your solution is going to become, because we're finding it at more and more points in between. So substituting our values in, we get y2 is equal to y1, which is the point we just found, 4.09, plus our step value, 0.05, times our function, 0.1 times the square root of y1, which is 4.09, plus 0.4 times our current x value, okay, remember, which is 2.05 squared. So if we calculate that out, we get that y2 is equal to 4.1842. And again, that is when x2 is equal to our previous x point plus our step value, which is 2.05 plus 0.05, or x2 is equal to 2.1. Okay, so we can stop there because we've now reached our value when x equals 2.1. Okay, so these methods use known variables or known points that in these equations to solve for points that we don't know the solution to. Okay. Our next method is known as the Runge-Kutta Method. It's much more accurate, but it's also much more involved. So the math is more complicated, but really it's just ultimately coming down to doing more calculations with algebra. So what Runge-Kutta does is, remember, we had something like this, and let's say we had a curve, okay? And we knew the point right here, okay? To approximate the next point, we did equal step values in between until we got to our value for that point. That was Euler's method. The Runge-Kutta method actually looks at the slope at 4 different spots in between the first point and the second point. So you picture you're finding the slope here, and then here, and then here, all the way until you get to that last point. And what you do is you're actually finding 4 different variables, and you're averaging those slopes, okay? Meaning you're taking one of the first slope and one of the slope closest to the next point, and 2 of the slopes in the middle. You can think of this as taking this as what's called a normal distribution of points, okay? Think of this kind of bell curve shape you would have seen in any stats courses that you've taken. So I don't want you necessarily to have to understand where this formula is derived. I just want you to understand how to calculate it. Okay? So remember, in Euler's method, we had our next point was equal to our previous point plus our step value times our function. In this case, we have our next value of y is equal to our previous value plus our step value divided by 6 times these 6 data points, okay? K1 plus 2 times K2, 2 times K3, and plus K4. And each of these can be solved by taking our function. Remember, we started with our equation dy by dx is f at x and y. So each of these values of k has to be found in order from K1 to K4 by substituting in specific values for x and y. So for the first point, the first value, K1, we substitute in the value that we know, okay, the initial value that we started with, x and y. For K2, we substitute in for x plus half the step value, which is h. For the y, we substitute y plus half the step value times our previous point, Okay, so it's looking directly previous. For K3, our x value is the same, x plus 1/2 of the step value h. And y, again looking previous, is the original y term plus 1/2 of the step value times K2, which is the point directly before it. This is why I said you had to do these in order. Our final point is going all the way to the end of that step value. So it's x, where x is the original value plus the step, and y is the original value plus the step value times your previous value for k. Okay? All of these are determining using previous values. We're trying to get inch closer and closer and closer to our next solution. Okay? Again, I will provide you these formulas. We're going to go over one example of these now, and you're going to see that this method takes a lot more time because there's more algebra involved, but ultimately they both rely on looking at the previous point in order to determine kind of where this curve's going, right? You're looking at the past, using data from the past to determine where it's going in the future or further down the slope or of the curve, okay? So let's look at an example. For the differential equation, dy by dx is equal to x plus sine of xy. It passes through the point xy is equal to 0, 0, in other words, the origin. Okay, thinking of our Cartesian coordinates. Find an approximate value when x equals 0.1 if the step value is h equals 0.1. So one thing you'll notice here, I set this question up like this on purpose. The step value and the value for x are the same, okay? So we start at 0 and we go to 0.1, and our step value is 0.1. So we're only doing these calculations once. And the reason for that is, again, you know, I talked about this when we talk about infinite series. If you can do the first set of calculations, there's no reason why you can't do future step values, okay? So showing you how to do it just for the first step value is sufficient, because I'd be showing you the same math twice. So remember, we'll start with our formula for this, okay? So y at n plus 1 is equal to y at n plus the step value divided by 6, and it's multiplied by all of these factors. K1 plus 2k2 plus 2k3 plus k4, okay? So just remember, for each one of those, you're going to now have to calculate them in order. All right? Our original point, x to the n and y to the n, is 0 and 0. Our step value is equal to 0.1. And like I said, we only have to do this once, because if we add our step value in, we're going to our next point, which actually 0, our original point, so x to the n plus 1 would be equal to x to the n plus our step, which is 0 plus 0.1, which is 0.1. Okay, so we only have to do this calculation once. So looking at this, we have to calculate K1, K2, K3, and K4. So K1 is simply the function at x to the n and y to the n, which we know are 0 and 0. If we do that, we get 0 plus sine of 0 times 0. So for any of these questions where we're involving especially decimals like this, make sure when you're doing your calculations that your calculator's in radians if it has a trigonometric function. Okay? In this case, sine of 0 is simply 0, so K1 is just 0. K2 is our function at, remember, this is different, okay? It's our original point xn plus 1/2 of the step value for x. For y, it's our original y point, y to the n, plus 1/2 times our step value times our previous k value, which is k1, which we know is 0. So this comes out to our function at 0 plus 1/2 times 0.1. And for y, 0 plus 1/2 times 0.1 times 0. Okay? If you calculate this out, you get that it's our function at 0.05 for x and 0 for y. Okay? Substituting that in, we get that k2 is equal to our x value, 0.05, plus the sine of x, which is 0.05, times 0. Okay? So 0.05 times 0 is just 0, and we know that the sine of 0 is 0. So this is just simply 0.05. Okay? We're going to keep doing this. Okay, we have 2 more to do. So k3 is equal to our function at x to the n plus 1/2 of the step value h, same as k2. Y is y to the n plus 1/2, again, of our step value, times k2, our immediately previous k value that we calculated. To calculate this out, we get f at x to the n, which is 0, plus 1/2 times 0.1. And our y is 0 plus 1/2 times our step value, 0.1, times our previous k, which in this instance is 0.05. If you calculate these out, okay, for k3, then you get our function at 0.05 and 0.0025. Okay? Substituting in these values, we get k3 is equal to our x value, 0.05, plus the sine of our x value, 0.05 times y, which is 0.0025. Okay? Again, making sure your calculators are in radians. When you calculate this out, you get 0.050125. So you're starting to inch to a different value here. Okay, it's taking a while. In this example, we have very small decimals, but you eventually get to that solution. So we have one more to do, which is k4. Once we calculate all these, we can simply substitute them back into this equation. And since we only have to do it once, remember, because our next incremental value of x is only one step value away, we'll be done at that point. So k4, our final value, is our function at x to the n, but in this case it's plus the whole step value, which is h, and y to the n plus, again, our whole step value instead of half, times our previous k value, which is k3. In this case, we have f at 0 plus 0.1, our whole step value, and our y is 0 plus our 0.1 times our previous value of k, 0.050125. Okay? So if you calculate that out, you get our function at 0.1 and 0.00500125. Okay? I know it's tedious looking at these numbers this way, but I always keep in mind, did this before you had calculators to just solve these. Okay? So substituting these values in, we get k4 is equal to 0.1 plus the sine of 0.1 times 0.00500125. Okay? If you calculate that out, you get 0.1005. Okay? So we have our 4 values of k. Now we can simply find our next point. So we get y1 is equal to our original value of y plus h divided by 6, or our step value divided by 6, times k1 plus 2k2 plus 2k3 plus k4, which is equal to y done is 0, plus our step value, which is 0.1 divided by 6, times all of our values for k. k1 was 0, plus 2 times k2, which is 0.05, plus 2 times k3, which is 0.050125, plus k4, which is 0.1005. If you calculate this out, we get that our next y point is actually equal to 0.005. Okay? Whew, that was a lot of algebra. But this method does find a far more accurate solution because it's constantly improving on its previous calculations when you look at calculating these k values, okay? By using the previous k value that you've already calculated. Okay, so that's all I had for this lesson. These are the practice exercises I recommend. What I will tell you is for exercise 31.5, when you're doing Euler's method and Runge-Kutta, just try completing the formula doing one step in the calculation. So sometimes these questions will ask you to find it for between x is 0 and x is 1.2 when your step value, sometimes they call it delta x, sometimes they call it h, it's the same thing. In this case, it's equal to 0.3. So you'd see that you have 4 steps to get from 0 to 1.2. I don't want you to do that. I just want you to calculate it for the first step. Okay, so you would look at calculating it for, in this case, when x is 0.3. Again, I come back to you're doing the exact same math, okay, just multiple times. If you have any questions, send me an email or send me a message on Teams. Thanks, everybody.